When we discussed minimum mean squared error estimation in the previous video, we ended up concluding that although the MMSE estimator is optimal among all possible estimators for theta, in the sense that it minimizes the mean squared error of the unknown parameter theta, it is an estimator that is difficult to apply. The main difficulty is that we needed to compute a conditional expectation of the unknown parameter given the data, and for that we needed a full statistical description of the dependency between the data and the unknown variable. We needed the joint PDF of the data and the unknown variable. In this video, we're going to present an alternative to the MMSE estimator, the linear MMSE estimator. We will see that the linear MMSE estimator keeps some of the good properties of the MMSE estimator while having a much simpler form. One of the ways that we can use to simplify the estimators that we will get is to constrain the functional form that the estimators can take. And this is precisely what we do in linear minimum mean squared error estimation. So, as we can see in this definition, the linear minimum mean squared error estimator is an estimator that has a particular form, which is described here. As we can see, the estimator is built by taking a linear combination of the data samples from 1 to n, which are weighted by a set of coefficients h1 to hn. And in addition, we have an extra offset coefficient h0. Now, we can discuss that the name linear is not exactly accurate. If we considered only the second term, this part, this is a linear transformation of the data vector x. In fact, we can write it here in vector form by multiplying vector h, which contains the coefficients h1 to h capital N, transposed, multiplied with the vector x, the vector of data, which contains the data samples from x1 to xn. This here, second term, it's a linear transformation of x. When we have an additional offset coefficient, the precise name for this transformation would be that of an affine transformation. However, for tradition in the estimation community, the estimator has always, or for a long time, been called the linear minimum mean squared error estimator, and therefore we will keep this terminology. So, we constrain our estimator to have this form in which we only need to select capital N plus 1 coefficients. Now, the value that these coefficients will take is that value which makes the mean squared error minimum. We will see in a different video that in order to derive the value of the coefficients, we will need to differentiate the mean squared error with respect to each and every one of the different coefficients, and then equate to 0. That would give us the coefficients that will either minimize or maximize the mean squared error. If we perform the minimization of the MSE with respect to the coefficients h0 to h1, we can find that the value of the coefficients which minimizes the MSE is the one presented here. So, we can see that the coefficient h0 depends on the mean of the unknown variable theta, which is subtracted the vector of other coefficients, h transposed, which is multiplying the expectation of the data x. On the other hand, the vector of coefficients h1 to hn is obtained by the inverse of the covariance matrix of the data, multiplied times the covariance vector between the data and the unknown variable theta. If we now plug in the expression of the coefficients into the expression of the estimator, we can write the final expression for the LMMSE. First, we'll substitute h0 And rather than writing it as a function of the vector of coefficients, I will also substitute the value inside. When I transpose the vector H, the covariance matrices will also be transposed, but we know that if we transpose the covariance matrix, this corresponds to simply switching the arguments of this covariance vector here, and then we get the inverse of the covariance of the data, multiplying the expectation of X. And then for the other term, the term in which we have H transpose multiplying X, again, we get the covariance between theta and X. It's a covariance vector. The covariance matrix of X, which multiplies the vector of data. I can group terms here and give it another form, which may be a bit more insightful, in which the estimator is simply the mean of theta, to which we add the following term. The expression of H transposed, which multiplies the data X subtracted with its mean. Now that we have presented the form of the LMMSE estimator, we are ready to discuss some of the properties that make it such a widely used estimator. First interesting property is that, as we can see from the calculation of the coefficients, only first and second order statistical modeling of the estimation problem is needed. What we mean by this is that rather than needing a full statistical characterization of the relationship between theta and the data X, in order to compute the optimal coefficients of the LMMSE estimator, we only need to know the mean of theta, the unknown parameter, the mean of the data, the covariance matrix of the data vector, and the covariance vector between the data and the unknown parameter. We can compare this to the case of the MMSE estimator, the nonlinear case, in which we actually needed the full joint probability density function of the data and the unknown parameter theta in order to compute it. It's much easier to obtain estimates of mean and covariance parameters rather than a full estimate of a joint PDF. A second interesting property is the fact that the computational complexity of the estimator is fixed and actually quite low. As we can see, since the estimator has an affine form, we only need to make, once the coefficients H0 and H have been calculated, for any new realization of the data, we only need to take n products and additions that will happen in the second term here when we multiply the vector of coefficients H, which has size n, times the vector of data, which also has size n. Therefore, only n products and additions are needed for every new realization of the estimator. Of course, this is given the case that the covariance matrices between the data and between the data and the unknown parameter are fixed and do not change on the fly during our estimation problem. Another good property is that the LMMSE estimator is an unbiased estimator, as the MMSE was. We can show this pretty easily if we try to compute the expectation of the estimator, and we write it in its form. This would be the expectation of H0 plus the expectation of H transposed times X. If I substitute H0 with its value, what I will get is the expectation of theta minus H transposed times the expectation of X. And here in the second term I can take the vector of coefficients out because it's a constant. That's multiplying the expectation of X. Now everything I have here in the first expectation are constants. So this is nothing more than the expectation of theta minus H transposed times the expectation of X which cancels out with H transposed times the expectation of X. So the expectation of our estimator, theta hat, coincides with the expectation of the unknown parameter. Therefore, the estimator is unbiased. As we know, the LMMSE estimator minimizes the MSE among all estimators which are affine, which have a form equal to this one here. And of course, this comes from the fact that the way we choose to compute the coefficients at H0 and H is precisely by minimizing the mean squared error. We can see that similarly to the nonlinear MMSE estimator, the LMMSE estimator fulfills its own version of the orthogonality principle. The LMMSE estimator fulfills that the estimation error is going to be uncorrelated with any affine function of the data X. What does this mean? Well, if we have a function f of X of the data which is affine, then it should have a form which is this one, similar to the estimator. It's just made of an offset coefficient and a linear combination of the data samples. The orthogonality principle for the LMMSE estimator states that the estimation error is uncorrelated with affine functions of the data. We can compare this again to the nonlinear case, the nonlinear MMSE, in which the orthogonality principle was fulfilled for any function of the data without restrictions. What we can interpret from the orthogonality principle for LMMSE estimator is the fact that since the estimation error is uncorrelated to any affine function of the data, it is not possible to reduce the estimation error any further by using affine functions of the data. And this is so because we have computed the affine function to minimize the MSE. Contrary to the nonlinear case, there could be other functions of the data for which the orthogonality principle is not fulfilled, and these would be functions which would be nonlinear. This means that even if we cannot reduce the estimation error any further by using affine functions of the data, we could potentially reduce it if we used nonlinear functions of the data. This would be the case in which the nonlinear MMSE estimator would be a better estimator than the linear MMSE. And finally, a nice property as well is the fact that we can compute the mean squared error of the LMMSE estimator upfront. This means that we can, just using the definition of the estimator, compute the value of the MSE, of the expected MSE. In fact, this value is equal to the variance of theta minus a second term which depends on the covariance of the data and the covariance of X and theta. The use of this property is that if we are considering implementing an LMMSE estimator for a given problem, we can know in advance, before implementing and testing the estimator, what is the level of accuracy that we can expect by applying an LMMSE. Therefore, we could decide whether the LMMSE is a good choice for the problem at hand, or whether we would rather use other types of estimators, for instance, nonlinear estimators. Another useful property of being able to compute the MSE upfront is that, for instance, if we are doing a test implementation in a simulation setup, we know what the MSE.R estimator should obtain. This can be helpful when, if we run simulations of our estimator and we average the squared error, we should see that the average squared error, if our implementation has been correct, should converge with enough realizations of the estimator to the theoretical one that we compute with this formula. To finalize our discussion on the LMMSE estimator, we finally look at the case in which we have not only just one unknown parameter, one unknown variable, but in fact we have multiple variables. We're going to employ an estimator that is sometimes termed the vector LMMSE. Now the name comes because we can group the unknown variables. In this case we have k different unknown variables, theta 1 to theta k. We can group them in a vector, theta of unknowns. And we would like to estimate them from a set of data, x, also stacked in a vector, with n components. And we again restrict our estimator, theta hat, with theta hat here is this time going to be a vector with k components, to have an affine form. We only want to do linear operations. As before, the objective is to find this affine function, affine estimator, such that the total mean squared error of the estimator is minimized. And for this case, we define the total mean squared error for the vector estimator theta hat as the individual mean squared error of each of its components. So just the sum of the mean squared error of each of the components of the estimator theta k, theta hat. Now, from this expression, we can already see clearly that in order to minimize the total mean squared error, we would need to minimize the individual mean squared errors of each of the components of the estimated vector. If we want to do so, and we want to do so using linear operations only, then the estimators for each k that minimizes the mean squared error is going to be the linear minimum mean squared error estimator, the LMMSE estimator that we have discussed before. Hence, in order to compute the optimal estimator, one needs only to stack individual LMMSE estimators into a vector form, and this would give us an estimator that would estimate a vector in which the mean squared error of each of its components is going to be minimum for the type of estimator that we have chosen, an affine estimator. If we do so, and if we actually write individual LMMSE estimators for each of the components here, we can find a pretty compact expression for the vector estimator, and very similar actually to the one for the scalar case, in which again the estimator is going to be the expectation of the unknown vector in this case, which will be added a term in which the zero mean version of the data vector is going to be weighted by, in this case, a matrix of coefficients rather than a vector. This is going to be a matrix because even if we have the same components that we had before in this term, this time the covariance between theta and x is going to be a covariance matrix, since the unknown variable theta is in this case a vector. Therefore, we multiply the covariance matrix of the vector of unknown variables with and the data with the inverse of the covariance matrix of the data itself. The result is going to be a matrix, and the result of the estimator is going to be a vector with k components. Similarly to the scalar LMMSE case, we can also compute the MSE of the vector LMMSE up front, and similar to what we defined before, the total MSE is going to be the sum of the individual MSEs. If we take the expression we had before for the individual MSEs of the scalar LMMSE case, we can write it in a compact form as the trace of a matrix that depends on the covariance matrix of the vector of unknown variables, to which we subtract this term on the right hand side, which is depends on the covariance of the data vector, and the covariance matrix between the vector of unknown parameters and our data vector. With this, we conclude the explanation of the LMMSE estimator.